order to solve linear system of inequalities, analyze the compatibility of these systems, and obtain the sets of all solutions of linear programming problems, we need to know and work with some algebraic structures such as polyhedral convex cone and polytopes, which, in spite of their practical relevance, are not well known. In this video, we introduce the concept of polyhedral convex cones. Just as vector spaces are the sets of vectors generated by all possible linear combinations of a generator set or a basis, cones are the sets of vectors generated by non-negative linear combinations of a generator set of vectors. The figure illustrates some examples of cones generated by one or more vectors. The first example is the set of vectors that are represented in a half line. The second is a vector space of dimension 1 generated by two vectors A1 and A2. This suggests for the first time that vector spaces are cones. The third is an acute cone generated by two vectors A1 and A2 that collects all the vectors contained in an infinite region shaded in yellow color. The fourth is a cone that is the sum of two parts, a one-dimensional vector space generated by vectors A1 or A2 plus a cone generated by vectors A2. Finally, the last one is a cone that is the sum of a one-dimensional vector space generated by A1 or A2 plus a cone generated by the vectors A3 and A4. It is interesting to indicate that every vector space is a cone, since it is evident that by duplicating the vectors of the basis and changing the sign of the duplicates, any vector can be generated from the basic vectors using only positive coefficients. Because if a vector has a positive component, we use the basic vectors, but if a vector has negative components, we use the change sign basic vectors. An interesting question is whether it can be generated with fewer vectors. The answer to this question is positive and surprising, because with just one more vector, it can be done. Therefore, if n is the dimension of a vector space, any vector in it can be generated with n plus 1 vectors using non-negative linear combinations. Furthermore, one of these generator sets is any basis extended with the vector that results from adding all the basic vectors and changing its sign. This result is of great interest and very surprising. It should be noted that every cone can be written in standard form, that is, as the sum of a vector space and an acute cone, such that their generator vectors, when they change sign, they leave the cone. In this slide, the acute cone is defined as that cone such that, by changing the sign of its generator, a vector out of the cone is obtained. It is important to identify the linear space by means of a basis and the acute cone by means of its edges. In another video, we provide an algorithm implemented in JavaScript to obtain the standard form of a cone in its simplest form, that is, providing the basis of the vector space and the edges of the acute cone if they exist. A cone can be defined by its parametric equations, that is, a set of equations that permit obtaining all vectors in a given cone and only them. It is interesting to say that we can also use the equations of a cone, but they will be defined and explained after defining the dual cone of a cone in another video. In the transparency, we show an example of parametric equations of a cone, which is based on the definition of a standard form of a cone. You can see that the first and second parts correspond to the vector space and the cone parts respectively, where the column vectors of the first matrix are a set of generators or a basis, while the columns of the second matrix are the acute cone generators or the edges, and the rows and the pies are real numbers and non-negative real numbers, respectively. Note that we can generate all vectors in the cone and only then, simply by choosing all possible combinations of real and non-negative real numbers as indicated. Finally, we can write the same expression in compact form using the Greek letters as subindexes to refer to the real and non-negative real numbers respectively. With this, we end this lesson and we invite you to see the next video dedicated to polytopes, which provide another important algebraic structure which, together with that of vector space and cone, complete the set of natural algebraic structures appearing when dealing with linear inequalities.